Assalamualaikum, my name is Nabiha Zaidi. Now I'm going to explain about isentropy efficiencies of steady flow devices. As we know, their irreversibilities accompany all actual processes and that their effect is always to downgrade the performance of devices. So it would be very useful to have some parameters that would be enable us to quantify the degree of the degradation of energy in these devices. There are discrete engineering devices working under steady flow conditions, such as turbine, compressors, and nozzle. Most steady flow devices are intended to operate under adiabatic condition, although there are easy heat transfer between the device and its surrounding. The ideal process that can serve as a suitable model for adiabatic steady flow devices is the isentropic process. What is isentropic process? The term isentropic means constant entropy. Also, a process during which the entropy remains constant is called an isentropic process, which is delta S equal to 0 or S1 equal to S2 for process 1 and 2. Isentropic process also the process is both reversible and adiabatic. The more closely the actual process approximates the idealized isentropic process, the better devices perform. It will be desirable to have a parameter that expresses quantitatively how efficiently an actual device approximates an idealized one. This parameter is the isentropic or adiabatic efficiency, which is a measure of the deviation of actual processes from the corresponding idealized ones.
Assalamualaikum, saya Muhammad Arsiban. Hari ini saya akan menceritakan akan satu ilmu tentang isentropic efficiency of nozzle. Okey, daripada definition daripada efficiency isentropic adalah efficiency isentropic of nozzle adalah bersamaan dengan actual kinetic energy of the nozzle exit divided by the isentropic kinetic energy at nozzle exit. This is the definition of the efficiency of the nozzle. Okey, untuk menerangkan apa maksud isentropic efficiency of nozzle ni, saya akan bagi satu contoh lah. Contoh nozzle. Nozzle ni adalah dekat the inlet of the nozzle is give to us 260 kilopascal, 707 degree Celsius and 80 meter second. Of the air and the outlet is the 85 kilopascal. The efficiency of the nozzle is 92%. So for this question, the question asks us to find the exit velocity, which is at this, and the exit of temperature. Is to find the exit velocity. So for the first thing, after get this question, we must plot the graph, and the graph is like the graph is the T versus the S, which is T in a Kelvin and the S in kilojoule over kilogram. So on the graph we get that the first point is at the 260 kilopascal, and the degree of the Kelvin is the 1020 Kelvin. So we plot at this at the first point. So the actual process of this nozzle is at this, which is we plot as the 2A, which is 2A at the 85 kilopascal, and the straight line from this point we call that the isentropic process, which is we plot as the 2S. So from the this question we can make the equation, which is to find the T2S, which is to find the temperature at T2S. We can plot this equation, which is equation is T2S over the T1 equal to the P2S over P1 power with the K minus 1 over K. So from the property table, we get that the K is 1.4 and the specific heat of the air is we get 1.005 kilojoule per over kilogram per Kelvin. So from this equation, we can find the temperature at this point. So we get the temperature at this point is 741.09 Kelvin. We get this. And then is energy in equal to energy out. So from this we get for the nozzle, we must include the kinetic energy. So the energy in, we can get the enthalpy 1 plus the velocity at the inlet equal to the enthalpy 2 plus the velocity at the isentropic. This is the velocity at the isentropic process. So from this equation, we can find the velocity at the isentropic process, which is we write as the V2S. After we derive equation, we get the H1 minus the H2S, which is we can change to the term ideal gas. We can change to the CP, the temperature 1 minus temperature 2S. So from this equation, finally we can get the velocity 2S is the 753 meter second. After we change the kilojoule per kilogram to the meter second. So the question asks us to find the exit velocity, which is to find the velocity at the actual process, which is at 2A. So 2A. So this is 2A. So we can use this equation, which is equation efficiency, which is actual kinetic energy at nozzle exit, divide to the isentropic kinetic energy at nozzle exit. So from the equation, we know that the efficiency of the nozzle is 0.92, and this is the term that we want to find, and this is the isentropic velocity. So from this equation, you can find the velocity at the actual process, which is 722.26 meter second. So it is the exit velocity of the nozzle. Okay, for the second question, which is the question asks us to find the exit temperature, which is the temperature at the T2A, which is temperature at this. If we want to find the temperature at this, so actually we can find the temperature using the isentropic efficiency formula, which is we know that isentropic efficiency formula is which is the enthalpy 1 minus the enthalpy 2A divided by the enthalpy 1 minus the enthalpy 2S, which is the basic equation for the isentropic efficiency. So based on this equation, we know that we use the air with the ideal gas, so we can change this term to the ideal gas, which is CP T1 minus the T2A for the first, and the second CP T1 minus T2S. So for the CP, the same CP, we can just ignore. So we know that the efficiency is 0.92, and the T1, we know that T1 from the question is 1020 Kelvin, and the T2A is the temperature we want to find. So for the denominator is the T2S. T2S is the temperature at the isentropic process, which is 741.09 Kelvin. So for this equation, we can find the T2A, which is T2A means the temperature at the exit temperature of the nozzle, which is we can find that the T2A equal to the 763 Kelvin, which is this.
Assalamualaikum warahmatullahi wabarakatuh. My name is Aina Nabila. I will explain about isentropic for turbine, which is also known as expansion process. So the formula for isentropic efficiency is actual turbine work over isentropic turbine work, which is also WA over WS. And from this equation, we can get H1 minus H2A over H1 minus 2S. How we get this equation is from the graph. So let's take a look at HS diagram. So first, we can see that there is two curve with two isobaric curve. So we take it as it is superheated vapor and it expand in turbine. Expand in turbine mean that expansion process is doing work to the outside and its enthalpy will decrease. So the start point of for isentropic expansion is from 1 to 2s, which is in vertical because of it has the same entropy, which is this s is the same, and the start point for the non-isentropic process, which is the actual process, is from 1 to 2a. So let's take a look at this equation. So for turbine isentropic efficiency for steady state adiabatic expansion process, the energy balance for it is E in equal to E out, and we will get this general equation. So we relate with the non-isentropic expansion or actual expansion. It is WA out equal to H1 minus H2A, and for isentropic expansion, WS out equal to H1 minus H2S, which is how we get this equation for the formula for the isentropic efficiency.
Assalamualaikum. My name is Putri Anis Murfika binti Megat Muhammad Munir. So today I'm gonna explain to all of you about the isentropic efficiency of compressor and pump. Isentropic is actually the entropy same and with the adiabatic process. Okay, before we go into detail about the isentropic efficiency of a compressor, we need to know the definition of itself. So, what is the meaning of the isentropic efficiency of a compressor? This is the ratio of the work input required to raise the pressure of a gas to a specified value in an isentropic manner to the actual work input. Okay, through the definition, we can conclude that the efficiency of the compressor is equals to isentropic compressor work over actual compressor work. So, for the symbol of the isentropic compressor work is Ws, while the symbol for actual compressor work is Wa. Okay, so this is the graph shows that the compression process H and against entropy means enthalpy against entropy. So this is entropy, and this one is shows the actual entropy. Enthalpy of entropy. This one is entropy, and this one is actual entropy. When the changes in kinetic and potential energies of the gas being compressed are negligible, the work input to an adiabatic compressor becomes equal to the change in enthalpy, and the equation for this case becomes efficiency of compressor is near to the enthalpy of 2s minus with enthalpy 1 over enthalpy of actual minus with enthalpy 1. When the changes in potential and kinetic energies of a liquid are negligible, the isentropic efficiency of a pump is defined similarly as a efficiency of pump is equals to work of entropy over work of actual, which is equals to the specific volume times with the differential of pressure over enthalpy of actual minus enthalpy 1. Compressors are sometimes intentionally cooled to minimize the work input. A realistic model process for compressors that are intentionally cooled during the compression process is a reversible isothermal process. Then, we can conveniently define an isothermal efficiency for such cases by comparing the actual process to a reversible isothermal one. So, this is the formula that I told before, which is efficiency. I told before the expression. Efficiency compressor is equals to work T over work actual, where WT and WA are required work inputs to the compressor for the reversible isothermal and actual cases respectively. Thank you.